So for our final example, we're going to revisit a problem that you've seen before, only this time we're going to solve it using both the Lagrange multiplier method and the direct substitution method. So our problem is to find a point on the plane given by the equation x plus 3y plus z equals 9. And we want to find the point that is closest to the point, maybe I should label this point P, which is equal to 0, 1, negative 1, 1. So visually, we've talked about this before, and we've used projections to be able to find it. We've done lines through planes to be able to find this minimized distance point. And now, we're going to use Lagrange multipliers to be able to do it. Now, using Lagrange multipliers, one of the problems is that they don't really give this in terms of what our f function is and what our constraint function is. So we actually have to create those functions. So in order to find the point on the plane that is closest to this point, closest means that we want to minimize the distance between this point and the plane. And so the function that we want to minimize is going to be a distance function. So consider, what is the distance from the point P equals 0, negative 1, 1, and any other point? Any point, and we're going to call that point x, y, z. So what is a function that measures the distance from this point to the point x, y, z? We're going to use our distance equation. So in general, our distance equation, it's just Pythagorean theorem. It's the difference in the x values squared, x minus 0 squared, plus the distance in the y values squared, which is y minus negative 1 squared, and the distance between the z values squared, which is z minus 1 squared, all square rooted. So essentially what this problem is asking is I want to minimize this distance function. And I also want to make sure that the point x, y, z lives on the plane. And that's going to be my constraint function. So if I make sure that I constrain my distance function so that my point lives on this plane and solve that using Lagrange multipliers, we'll be done. There's one trick. Minimizing this function is a messy thing to do. So instead of minimizing the distance function, I'm actually going to minimize the distance squared function. This is sort of cheating. Cheating is the wrong word. This is a trick that I might not have thought of because taking derivatives of this function is super messy and I don't want to deal with that. So instead I'm going to take derivatives of the squared of this function. So this d squared function is going to be my f function. And in this case, it's an f function of 3 variables. And my constraint function, my g function, that's also a function of 3 variables. We aren't phased by using 3 variables, though. My g function is going to be exactly the equation of the plane, which is my constraint. 3y plus z equals 9. And I can label these. This is my constraint, or our road, and this is our function, which is our mountain. Now I'm mixing metaphors, but you get the idea. So what's our method of Lagrange multipliers? I'm going to take the gradient of f and set it equal to some constant multiple lambda times the gradient of g. So the gradient of f in this case, I'm taking the derivative of each of these components. I get the derivative of this. I'm not going to simplify it, I'm just going to do it because the derivative with respect to x is just 2x. The derivative with respect to y is going to be 2 times y plus 1. I could multiply all this out, but I think it's easier to use chain rule. So I'm using the polynomial rule where the 2 comes down in front, multiply this by the inside stuff, times the derivative of the inside stuff, but the derivative of this function in this case is just 1. And then finally, the partial derivative with respect to z is given by 2 times z minus 1. And that's going to be set equal to lambda times the gradient of my g function, which is an easy gradient. It's, in this case, actually exactly the normal vector of this plane. The partial with respect to x, the partial with respect to y, and the partial with respect to z. And as always, with Lagrange multipliers, we do this work, and we're going to have to come up with a system of equations, and then we're going to solve that system of equations. So in this case, we get that 2x is equal to lambda by setting the x components equal to each other. We also get 2y plus 2 is equal to 3 times lambda. And we get that 2z minus 2 is equal to lambda. And I'm going to use the fact that 2x is exactly equal to lambda, and I'm going to plug it into these to solve. But remember, these three equations, I have 4 unknowns. I have an unknown of x, an unknown of y, an unknown of z, and an unknown of lambda. I need to make sure that I also take into account my constraint. So I also need to have the equation x plus 3y plus z equals 9 to be able to solve this. And I'm going to erase something over here. Maybe you don't like me to erase all this stuff. Too bad. You can go back and watch it on the video. I need more room to be able to solve this system of equations. So solving this system of equations, I get the fact that 2x is equal to lambda. I'm just going to plug that in. That means that 2y plus 2 is equal to 3 times 2x, because 2x is equal to lambda. And I can simplify this a little bit. I'm going to divide everything by 2. That's my quick method, because then I get y plus 1 is equal to 3x. And solving for y, that means that y is equal to 3x minus 1. Next, I'm going to take my same lambda and plug it into my z equation, and I see that 2z minus 2 is equal to lambda, which is equal to 2x. Again, I can divide by 2, and I get z minus 1 is equal to x, or z is equal to x plus 1. So I have y in terms of x, I have z in terms of x, and now I can use both these things to plug into my final constraint function, because that means that x plus 3 times y, which is 3x minus 1, plus z, which is x plus 1, has to be equal to 9. And I can solve for x. This is going to be x plus 9x plus another x is 11x. And then I also get minus 3 plus 1 is minus 2 equals 9. I add 2 to each side, and I get 11x is equal to 11, or x is equal to 1, which is great, because now it's easy to go back, and if x is equal to 1, that means that z is equal to 2. And if x is equal to 1, that means that y is equal to 3 minus 1, which is also 2. Ta-da! We're done. So we found out that this set of Lagrange multipliers gives us a solution when x is equal to 1, y is equal to 2, and z is equal to 2. 1, 2, 2. And if I wanted to, which I probably should, which I'm not going to, I could plug this point back into my distance function to find out that this actually is the point that minimizes. From a geometric sense, it makes sense that if we were only going to find one max or min point, because all of the others just keep getting bigger and bigger and further away, there is no maximum distance away from a point. There's only a place that's a minimum distance away from the point. And that's the place that we just found. So we just solved this problem using Lagrange multipliers. Now we're going to solve our maximization with constraint problem, only this time we're going to do it through substitution. And you can decide which one you like more in this case. So we're going to have the same functions as we had before, that our distance squared function is going to be the function that we want to maximize or minimize. And this is representing the distance from the point x, y, z, some generic point, to the point 0, negative 1, 1, which is the point P that we want to get close to. But we need to make sure that our point x, y, z lives on this plane. So we have this constraint function. And recall, for this method, what I'm going to do is I'm going to solve for one of the variables in here and substitute it back into the function that I want to maximize or minimize. In this case, I'm going to let x equal 9 minus 3y minus z. I solve for x and then plug that into this function. You could solve for whatever variable you wanted to. So the function that we're trying to minimize, I guess before I called it f of x, y, z, which is our d squared function, is going to be given by x squared, which in this case is 9 minus 3y minus z squared, plus 9 plus 1 squared plus z minus 1 squared. So this is the function. Now instead of being a 3-variable function, I've turned it into a 2-variable function. And I want to find the maximum values and the minimum values of this 2-variable function. And in this case, we're only going to find the minimum values because that's the only place that makes sense in this geometric situation. So how do I minimize this function? I'm going to take the partial derivatives and set them equal to 0. So taking the partial derivative with respect to y and setting it equal to 0, I get, taking the partial derivative, instead of multiplying all this out, I think it's easier to use chain rule. So I'm going to get 2 times 9 minus 3y minus z. So that's the derivative of the outside of the function, times chain rule, the derivative of the inside. The derivative of y in this case is negative 3, plus, again using chain rule, 2 times y plus 1 times the derivative of the inside, which is just 1. I guess I can multiply it by 1. And then the z is just a constant, so it goes away. I have this missy thing. I need to set it equal to 0. The first thing I'm going to do is divide everything by 2. We did that before. Excuse me. So then I get 0 is equal to 9 times negative 3 becomes negative 27 plus 9y plus 3z plus y plus 1. And so this gives me 10y, 26 is equal to 10y plus 3z. Great! That's one equation. This is when our partial derivative with respect to y is set equal to 0. Now we have to take our partial derivative with respect to x, z and set that equal to 0. So I'm going to look at f sub z, the partial derivative of my function. Maybe I should highlight this. This is the function that we're looking at. We've plugged in our constraint. The partial derivative of our distance function is given by the derivative of this chunk, again, is going to be 2 times 9 minus 3y minus z times the derivative of the inside with respect to z, which is negative 1, plus this term becomes 0, and this term is 2 times z minus 1. Can you guys see that on the camera? I'm going to check before yeah, there's plenty of space. Good, good, good. So this is our derivative with respect to z. In order to minimize this function, again, we have to take this and set it equal to 0. Set our partials equal to 0. Again, I can divide everything by 2. And I end up with negative 9 plus 3y plus z plus another z minus 1 has to be equal to 0. So I have 2z. I get 3y plus 2z is equal to 10. 2 equations, 2 unknowns, I solve. I'm going to solve for z, and I get that z is equal to 10 minus 3y divided by 2. I take this, plug it into the other function. There are a number of ways that you can solve 2 functions and 2 unknowns. This is the way that I'm doing it today. And I'm going to get 26 is equal to 10y plus 3 times z, which is 10 minus 3y, all divided by 2. Phew! And I simplify this, and 26 is equal to 10y plus 30 divided by 2 is 15 minus 9 halves y. So 20 halves y minus 9 halves y becomes 11 halves y plus 15. I subtract 15 from both sides, and I get 11. And I get y equals 2. This is a bunch of algebra. I expect you to be able to do algebra on your own, probably far better than I can do algebra right now in my current state. So we just get y equals 2. I can plug that back into solve for z, and I find that that means that z equals 10 minus 6, which is 4 divided by 2, which is 2. And we get our original solution. Y equals 2. Z equals 2, and plugging into our original constraint, we get that x equals 1. So we found the same solution both ways, which is great. One way, doing Lagrange multipliers, where we take gradients, set them equal to each other, and solve that system of equations. Method number 2, solving for one of the variables, plugging it back into the original function, and then taking the partial derivatives, setting them equal to 0, and solving for what the values needed to be.